Welcome to our lecture online. Our next topic is kinetic and potential energy of a satellite in orbit, but this time it's around an elliptical orbit, not a circular orbit, which means when it's closer to the Earth, it's moving faster. When it's far away from the Earth, it's moving slower. So let's say we know the velocity when it's over here. We can figure out the potential energy over there. We can figure out the potential energy over here, and then we can figure out the kinetic energy and thus the velocity at the location far away from the Earth. All right, so again, just like we did in earlier chapters, we can say that the energy initial, or the kinetic energy initial, plus the potential energy initial equals the kinetic energy final plus the potential energy final. And since we're looking for the velocity, let's call this velocity final, we then want to know the kinetic energy final of that equation. So moving everything over to the other side, we can say that kinetic energy initial plus potential energy initial minus potential energy final will equal the kinetic energy final. So all we have to do is find the kinetic energy initial, and potential energy final to find the kinetic energy final. Well, that's actually a lot of work when I say that's all we have to do. It's straightforward, but a lot of work. So let's take it one at a time. Kinetic energy initial is equal to 1/2 mv initial squared. So it would be 1/2 times the mass. The mass would be 1,000 kilograms. And the velocity was given to be 7,615 meters per second. 7,615 meters per second. And we have to square that. So let's find out what our initial kinetic energy was. So it would be 7,615, square that, and multiply times 500 equals, and we get this is equal to 2.90 times 10 to the 10th joules. That looks familiar because obviously that came from our previous problem, number 18. Okay, next we need to find the potential energy at that location. And the potential energy at that location, potential energy is equal to, initial is equal to minus Gm big M over R. Now, if I remember right, that should be equal to double that and negative, but just let's see if that's indeed correct. So that's equal to minus 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Okay, that is times 1,000 kilograms, and times the mass of the Earth, which is 5.98, times 10 to the 24 kilograms. And the whole thing divided by the radius, that would be the radius of the Earth, plus the height of 500 kilometers. So that's a total of 6,878,000 meters, and we don't have to square that. So that would be the potential energy at its initial position. So 6.67 e to the 11 minus times 1,000 times 5.98 e to the 24, and divided by 6,878,000 equals, and sure enough, that's equal to minus 5.80 times 10 to the 10th joules. Remember that the potential energy and kinetic energy differs by factor 2. The potential energy is double as much as the kinetic energy, and it's a negative quantity. So now you kind of see how that works. But now, of course, to find the potential energy there, we have to plug in a different number. So potential energy final is equal to minus Gm big M over R final. So that's equal to minus 6.67 times 10 to the minus 11 Newtons meter squared per kilogram squared times 1,000 kilograms times 5.98 times 10 to the 24 kilograms. That's the mass of the Earth. And the whole thing divided by now the new radius, which is going to be the radius of the Earth, plus 2,000 kilometers. So that's 6,378,000 plus another 2 million meters. So it would be 8,378 instead of 6,378. All right, so let's plug those numbers in. Actually, yeah, that would be 6.67 e to the 11 minus times 1,000 times 5.98 e to the 24th divided by 8,378,000 equals, and that would be equal to minus 4 0.76 times 10 to the minus 10 oh, not minus, plus 10 joules. Now, for a moment there, I was a little taken aback. I ended up with a smaller number, but that makes sense because the higher up we are, the smaller the negative number becomes, which means the bigger the potential energy. So again, be careful. Those negative signs really play tricks with your brain. So even though it looked like the number was smaller, it actually means the number is bigger, right? Because the smaller negative number is really a bigger quantity. So this potential energy final is bigger than this potential energy initial. All right, now we can see that to get the kinetic energy final, that is equal to the kinetic energy initial plus potential energy initial minus potential energy final. So the signs are very important here. Let's match up the numbers that we have. Kinetic energy initial was a positive 2.90 times 10 to the 10 joules. Plus the potential energy, but potential energy is negative, so it's plus a minus 5.80 times 10 to the 10 joules. And now we subtract from that the potential energy final, which is a minus 4.76 times 10 to the 10 joules. And that will give us the kinetic energy at the faraway point. Okay, so this minus this is this minus, so we have 2.9 e to the 10th. And so we add to that this quantity right here. So 2.9, that's minus e to the 10th, and we add to that plus, because the minus times a minus a plus, 4.76 e to the 10th equals, so we get 1.86 times 10 to the 10th joules. All right, so let's compare this kinetic energy to the initial kinetic energy. It's smaller, and does that make sense? Well, if the spacecraft, the satellite, goes farther away from the Earth, it gains potential energy, and therefore it has less kinetic energy. So less kinetic energy compared to the initial is indeed what we would expect. So that seems to make sense, kinetic energy final. And now we have to find the velocity, so we're going to use the equation that kinetic energy final is equal to 1/2 mv final squared. Solving this for v final, we can say v final is equal to 2 times the kinetic energy final divided by the mass. Of course, we have to take the square root of that. So now plugging in those numbers, this is equal to the square root of 2 times the kinetic energy final, which is 1.86 times 10 to the 10th joules, divided by the mass of the satellite, which is 1,000 kilograms. So divide this by 1,000, multiply times 2, and take the square root, and we now have a velocity of 6,099 meters per second. So notice, it is not as straightforward as before working with energies, but the concept is still exactly the same. You add up the initial kinetic and potential energy, and that always has to equal the final kinetic and potential energy. So in this case, we solve for the kinetic energy final first, then we use the equivalence in 1/2 mv squared, solve for v final, and that's how you find the final velocity at that location. So hopefully this really helps you figure out how to work with satellite motion in using gravitational potential and gravitational kinetic energies.